Hello. All right, I've got 5 past the hour, so it's time to get started. There's quite a bit to get through today. I'm excited to see you all as well. So the thing that we met yesterday was the concept of the Riemann integral in multiple dimensions, and today we're just going to tease that through and basically wrap up kind of all the theory you need to be able to handle these problems, because there's a few little odds and ends to do. Because what we discovered yesterday is that if you have some rectangular domain, you can partition it off in both of your directions. You can add up the signed volume underneath that curve for each little rectangle, and you can get an equivalent quantity for what you know as the one-dimensional Riemann integral. And this was all very nice, and the derivations, as we discovered, basically work the same way, except that they are volumes rather than areas. Fine. We went through the details. I'm not going through it again. I just wanted to start on that because it was a nice summary thing. But of course, as we mentioned at the end, the problem that we have is we showed that for rectangular domains, and this is a great many things, but it is not a rectangle. So it seems like the theory that we have derived doesn't quite work. Someone suggested yesterday, what about if we break this area into a bunch of very, very small rectangles and take the limit as that goes to 0? And that will work, but that's not actually quite what we're going to do. You have to be careful about making arguments like that. For instance, that would work to calculate the area, but it would not work to calculate the perimeter. You can test this yourself. If you break this into little squares, infinitesimal, then actually you get the wrong answer for the perimeter and the limit. So you just got to be a bit careful about making geometric arguments. We are instead going to try something a bit bigger, and I'm going to say, let's make it a rectangle. Okay, now it's a square. How do we make a square a rectangle? What's something nice about single variable integrals and when they exist? That's okay. This is a question I didn't necessarily expect, but remember, you can take the single variable integral of a function with discontinuities. That's a thing you're allowed to do. So what we're going to do is, let's say everything is a rectangle, and in fact D is just a subset of some larger region R. And we're going to define a new integrand, which is f of xy, if xy is in my original D, but 0 if xy is not in my original domain. And now I have a nice rectangular region. Okay, so the integrand's a bit discontinuous, but that doesn't matter at all. And we can just continue like we did. This is literally the whole theoretical setup. That's all we needed to do. Because now we can say, okay, well, in this case, I know, let's say this is A to B in the x direction and C to D in the y direction. Then I know that this can be the integral from C to D, integral from A to B, of f tilde xy dx dy. And that exists from everything we did yesterday. This is a perfectly reasonable thing to do. Exists from yesterday. So now we're in pretty good shape. Except looking at this integral from A to B, well, we're trying to integrate from A to B along here. So from A all the way over to B, and if I just gave you this as a one-variable integral problem, you would know exactly what to do. You would say, well, since it's 0 outside of the region D, then I can actually just evaluate this integral from here, which I'm going to call P, but I'm going to leave myself some room, to this point, which I'm going to call Q. Except there is a difference between P and Q and A and B, which is that it doesn't matter where I am in Y, A and B are the same. But P and Q depend on Y. So now we are integrating, and what we're going to do is say, well, this actually reduces to The integral from c to d, that's fine, or more or less at least the bits where there is some domain, but we don't have to worry too much about that. The integral of 0 is 0. Of the integral from p of y to q of y of f of xy dx dy. So our iterated integral has changed, and this will work. Everything we've done here, this little last trick, is just something we can do using single variable arguments. Our integrand is 0 outside of this. Of this. Now, when we set up these problems, we're not going to do this every time. We're going to start from here. This is just the theoretical setup that convinces us that it's okay to do that. So you'll never set up a problem like this. You'll jump straight to this point every time. So normally we will start here. I'm writing normally just in case there's an exception that somebody yells at me about, but I can't think of one. We will normally start here. So this is fine, and this seems like it hasn't broken anything I taught you yesterday, but actually it sort of has. So there is a little complication that this introduces. So let's actually run through this example, and let's see for ourselves what happens. Okay, so I'm going to say my domain is the unit circle, and my integrand is x squared times y squared. And if I go into Mathematica and plot that, what I see is something that is 0 on the two axes and kind of goes up and back down in each quadrant. So you kind of got a flower with 4 petals that grow off to infinity, like all flowers. So it makes sense, the thing. So we can kind of imagine what we're trying to see is that we'll get 4 times this integral component here. Okay. So the integral of our domain, what I'm going to do is pin this in a box between -1 and 1, just to make sure there's no leftover bits and pieces. So here, I'm going to integrate y from -1 to 1. And let's make this iterated for now, but this is about when we're going to stop using brackets to denote the order and just trust you to be able to read that off, but we'll do one more of these. So I'm going to go from -1 to 1. But within that, I'm going to be going from some sensible p of y to some sensible q of y. Okay, so remember these are allowed to depend on y. So the lower bound is minus the square root of 1 minus y squared. I'm going to want to leave space there, but you can see hopefully that this point is minus 1 minus that thing, and this point is plus 1 minus y squared. Our integrand, nice and easy, x squared y squared dx. And now it's just a matter of doing the integral. And as we find when we do the mechanics, the fact that there is a y in here isn't going to cause us any problems at all, yet. So we'll just run through the analysis. This is equal to -1 to 1. Integrate that up, x cubed on 3, y squared is a constant. From minus square root of 1 minus y squared to square root of 1 minus y squared dy. And that's a single variable integral. So we get the integral from -1 to 1 of 1/3 y cubed 1 minus y squared to the 3 on 2 dy, which is, if my calculations before this class were correct, pi on 24. Wait, sorry? Oh, did I evaluate it? That does make more sense. Yep. It does seem likely. We can all check integrals after the fact. Point being, you evaluate the inside integral first, and it gives you a function of y. No, I don't think I have evaluated it. Yeah, there's still y in it. We're going to leave it like that and trust that I did this right before class, but you all remember how to integrate. Really feels like that should be a y squared, right? That's what's wrong. Yeah. Good. Every single person who went through the HSC is better than single. If this is about why my integral is wrong, we're moving past it. What's the question? Sorry? I don't know what your question means. Isn't what? Sorry? Is it 2 over 3? Could be 2 over 3 or 2 over 9. Probably the number is wrong, but do the integral, convince yourself that it's right, and I will make sure when it's uploaded that I can do one variable integration. Point being, you can power all the way through to an answer. All right, you're all chattering, I assume, about the integral, but let's keep going because this is not the point. We have lost something. By doing it this way, we can't do something that I taught you how to do yesterday. Yesterday, I said you can do these integrals in either order. You can swap these integrals and it doesn't cause you any problems. But that's not true anymore because it doesn't make sense to swap these two integrals now. It doesn't make sense to integrate from square root of 1 minus y squared to square root of 1 minus y squared. And then integral minus 1 to 1 x squared y squared dy dx. Because I'll integrate this thing up, I'll lose my y variable, but then I'll be integrating something with respect to x, but my answer will have y's in it again, and that stops making sense. So as soon as you play this trick, the thing that you give up is the ease with which you can swap these integrals. Because I'm no longer integrating over the whole region. In fact, what I'm probably going to want to do is something like, if I'm going to swap the integrals, an integral between these points, which if I had lined those up correctly, good. From some r of x to s of x. So now, when I swap the integrals, I'm going to go from one fixed integral and one y-dependent range to one fixed integral and one x-dependent range. Swapping the integrals becomes a bit more of an exercise in geometry once you start dealing with non-rectangular regions. So let's try and do this, but let's do this a little bit more carefully and just setting up the integrals to see how this should be done. Okay, so here I had y equals minus 1 to 1 dy. And you can see that the outer bounds are constant. And I'm going to have my inner integral from x equals 1 plus y squared to y squared, where these are y-dependent. Now, a thing that I will do sometimes when we have multiple integrals and it's a little unclear what our integration variables might be, is actually writing them in our integral. This has never been an issue before, and if you're good at bookkeeping, is never an issue for you. However, it is a helpful thing to do for me to write it out this way, and I will often do that, particularly later on when we start to change variables a lot. So don't feel like this is something you have to do every time you do an integral. Often it is just me flagging what pairs with what to make sure that you are extra sure of that. Okay, so changing the order doesn't just mean switching those integrals around anymore. It means instead of integrating horizontally then vertically, we are going to integrate vertically and then horizontally. So we are going to start at some r of x and integrate all the way up to some s of x. So now my first integral is going to be with respect to y, and it's going to go from minus 1 minus x squared to 1 minus x squared. And now I've moved the dy inside, and these are the bounds in y. Now they're the same form as it looks like the one above, but that you don't just swap y and x. That's just to do with the symmetry of the problem. That normally won't happen. So normally you will get very different looking functions in your integral bounds. Nothing about the integrand changes. We're only changing the bounds, so the integrand stays exactly how it was. But now our dx integral is no longer y-dependent because we sweep over the whole region from x equals -1 to 1. So there's a bit of geometry. It helped that we had a surface to look at. It helped that we had a picture. When it comes to swapping integral domains more than anything else, having a picture is really, really useful. Now I'm going to give you an example and give you 3 minutes to tackle it yourself, and then I'm going to work through it. And this is not symmetric, so you should expect your bounds to look a little bit different. So I'm going to say horizontal cuts and vertical cuts, and I'm going to remove the thing I forgot to erase. So what is this curve? This curve is y equals x squared, which, I don't know, you could possibly say is x equals the square root of y. I don't know if that'll be helpful or not. Maybe it will. So have a go at that. Take a couple of minutes. Yes? There is not a plus or minus because this is only positive. So if you were inverting the equation, you would get a plus or a minus, but the minus would refer to a different curve that goes down this way. X equals minus. No, it would refer to the curve that comes up this way. Pluses or minuses are not some immutable truth. You actually have to think about the geometry of the curve. While you're doing that, I'm going to quickly work that example on the previous page and get all my y's right. I am relatively confident that there should have been a 2 here. It is possible that that may be pi on 12. It doesn't matter.
It's pi on 24.
It is pi. It's pi on 24. Thank you, Stella.
24.
Good.
Because I use polar coordinates.
We may do that later today. All right, I want to give you another minute and a half, 90 seconds. Forty-five seconds. All right, wrap up what you're doing, and then you get to listen to me again. 10, 9, 8, 7, 6, 2, 1. All right, so I wanted you to formulate this both ways, and we're going to start with horizontal cuts. So horizontal cuts, by which I mean, I want you to first integrate horizontally in some y-dependent way from x equals p of y to x equals q of y. And then what we find is our inside integral has to go from, well, at this point we have x is equal to the square root of y, and it continues all the way across to 1 dx, and our outside integral now can just sweep over the entire rectangle. So we get y going from 0 to 1. So this corresponds to the green curve. Our integrand never changes, so that becomes x plus y dy. And if you evaluate the inside integral, given my track record, there's about a 50% chance that the answer is this, which, when you evaluate that out, is 7 over 20, if I did my calculations before correctly. Okay, but we could also do it the other way. So, can someone volunteer for me what the inside integral is if we are going to integrate vertically from some r of x to some s of x? Hands up, someone brave. Yes. 0 to x squared, very good. So we want to start from y equals 0, and we want to go up to x squared. I'll do that below. So we want to go from 0 to x squared, and that is dy. And this corresponds, of course, to the magenta curve. And now x can just go from 0 to 1. Our integrand can stay the same. dx, we evaluate that first integral, and we get the integral from 0 to 1 of x cubed plus x to the 4 on 2 dx, which is equal to 7 on 20. Same thing, which suggests that I've either gone wrong exactly the same way both times in my preparation, or I got these two right. A shake of the head. Did I get it wrong? No. Okay, good. So you can see these are two ways of doing the same integral. Why could we possibly need two ways of doing the same integral? Just pick one, Chris. Well, let's talk a bit. Reversing the order of integration changes the bounds in a way that it didn't when you have rectangles, which is to say rectangles are nice. I would like you to remember that fact for the second hour. It does not change the integrand in any way. That's nice. Sometimes an integral is completely intractable in one direction and very, very simple in the other. That was true when we had rectangles. That is even more true now. Which is to say, sometimes making this change can take us from something we can't write down an answer to something that we can, not just because it's hard, but because it's algebraically intractable. My high school math teacher told me that you differentiate with your head and you integrate with your heart. That is true here as well, right? Like, there's as much luck as judgment when it comes to integrals. Sometimes you just try things, and now you have more things to try, because you have all the things you can try in one order and all the things you can try in the other. Now, I want to reassure you of something. This class is not about me throwing difficult integrals at you. The complexity of what I do is never going to be, oh, pick this random complicated transform. There will always be breadcrumbs that lead you in the right direction. You have been thoroughly tested on whether you can do one variable integration. That said, the be able to do all of the standard integrals, polynomials, trigonometric functions, exponentials, all of those things, because I'm going to take it as a given that you can. But I'm not going to expect you to find some inverse trigonometric substitution, because I can't remember them, and that would not be fair. Some math students hate drawing. I get it. We love algebra, we love symbols, we love moving things around. The objects we study in this class are objects, and drawing them helps us understand them. You were all, I think, able to pretty easily see what these bounds were, but if I just said the region is the region between the x-axis, x equals 1, and the curve y equals x squared, probably some of you might have struggled to go from just that description to these integral bounds without sketching out the picture in between. Draw a picture. It's always helpful. So whenever you can, draw a picture. You won't regret it. What if I don't give you a picture? What if I just give you an integral? And that's what I'm going to say here. In this case, what if I just hand you this thing? Integral from 0 to 2, x1, xy, dy, dx. Well, we're going to do three things, and then we're going to see if they all agree with each other. First, I'm just going to evaluate that. This is an integral I can evaluate. I don't have to think about the region. That is a series of symbols we can move around to get an answer. So let's do that. Integral from 0 to 2. Inside integral is the integral from x to 1, xy. So let's evaluate that, and we get x squared y squared over 2 from x to 1. Oh no, I integrated with respect to, sorry, x. X squared over 2 from x to 1, which is equal to the integral from 0 to 2 of x over 2 minus x cubed over 3 over 2 dx, which is equal to minus 1. Okay, good job, full marks, 10 out of 10. Now I'm going to say, well, I'm going to want you to reverse the integration order and show that they get the same result. But reversing the integration order, it's not so simple as just swapping those, because we know that the bounds have to change from being in terms of x to being in terms of y. You might be able to just invert the lower thing, but actually we want to be a little bit careful about this. So I've started drawing out the region below. So my x is going to go from 0 to 2. So I've swept out my x from 0 to 2. My y is going to go from x to 1. So here, my y is going from x to 1. Here, my y is going from x to 1. And you can see that the region described by this integral sweeps out this interesting double triangle. Okay, so I think, great. So my x limit takes me here. So my x limit, and these things in here are my y limits. If I want to do the third step and reverse the integration order, then what I want to do is sweep out all of y. So this becomes my y limit. But these things in here become my x limits. So to sweep out this area, I need to integrate horizontally, not vertically. So let's then follow through on this and make sure that both integrals give the same answer. Sorry, there we go. All right. So I've got my integrals, and you can see it actually makes sense in this flipped coordinate. So let's just do this as two separate triangles. So my first triangle takes me from y equals 0 to 1. So here is number 1. And x goes from 0 to y. Integrand doesn't change. Dx, dy. Plus my second integral, where you can see y is going to go from 1 to 2, and x is going to go, it's going to start at y, and it's going to go all the way to 2. X plus y dx dy. So using my geometry, I've set up the integral. Just a quick vote, and ignore the text at the bottom of the slide. Who thinks this is going to go great? Yeah, okay, good. All right, let's find out why you are all correct. So I do my first integral, my inside integral, x squared over 2 plus y from 0 to y dy, plus my second integral, x squared over 2 plus xy dy, which is equal to the integral from 0 to 1, 3y squared over 2 dy, plus the integral from 1 to 2 of 2y minus y cubed over 2 dy equals 5 over 4. 5 over 4 and minus 1 are different numbers. I want you to turn to the person next to you and tell them why I'm stupid. No, it's not stupid. This is an easy mistake to make, but tell them what went wrong. Five, 4, 3, 2, 1. Stop. Hands up who heard a sensible answer. Hands up who thinks that the person told them the right answer. Okay, a few of you. Hands up who is willing to volunteer the answer their friend told them. Yeah, Wilson.
The first integral, because you're integrating.
Amazing. Perfect. Thank you. Integrals are directional. This integral is integrating in a positive direction. It has a positive signed area. But this one was going from x to 1. It has a negative signed area. So it's going to multiply the contained volume by 0. The way we constructed this integral was that it went from 0 to y, but then we constructed the second integral. Yep, if my iPad works. But then we constructed the second integral. Excuse me. Nothing like a bit of tech issues. But then we constructed the second integral so that it went in the positive direction. So we constructed both integrals to be positive, which means they both have positive signed area. Signed area was very simple in one dimension. You go right or you go left. You have to be a little bit more careful about signed area when you start swapping around the regions of integration. What we should have written was the integral from y equals 0 to 1, integral from x equals 0 to y, x plus y dx dy, minus, let's do that in red, minus the integral from y equals 1 to 2, integral from x equals y to 2. Or we could have done x equals 2 to y. That would have been fine as well. X plus y dx dy. And this does, in fact, give the correct result. You should confirm this for yourself. If you're watching the video 2 days before the exam, pause the video and show that for yourself. Okay. So this is nice and easy. It just means that we need to be a little bit careful about geometry. We're going to keep powering on and do a coordinate system which I think you've met before. So here I've just written out this integral. I've said integral from 0 to cos theta, integral 0 to pi on 4, cos theta dr d theta, and then reverse the order and get the same result. What is the name of this coordinate system? Polar coordinates. Of course, it's only polar coordinates when we put an interpretation on it. At this point, it's just a series of symbols that we can churn through. And in fact, we don't really need to think about what it means at all until we want to switch the order. So, we get that integral. We can't remember anything about geometry. Let's just churn the algebra. Do the inside integral first. Integral from 0 to pi on 4. of integral of the inside, which is r cos theta, from 0 to cos theta d theta, is equal to the integral from 0 to pi on 4 cos squared theta d theta, which is equal to pi on 4. Okay, so you do that, you churn the algebra, you move the symbols around, you get the numbers that give you the marks, you get your dopamine hit, and everybody is happy. But then we want to reverse the order of integration. Now, once you get really good at this, like I've said, you can start to think about, well, okay, so that's r equals cos theta, so assuming I don't want to do anything too fancy, I can get the inverse function of that, and that will work. But we want to look at our picture, because we've just learned if we do that and we aren't careful, then we can end up doing things like reversing the sign direction when we're not paying attention. So our interval in theta is 0 to pi on 4. So that is this thing here. Theta goes from 0 to pi on 4. Now, you probably thought I was going to do this out in polar coordinates. But remember, that is just one perspective. In some sense, we're looking at a rectangle in r theta space. So the geometry you do your integral in doesn't necessarily have to be the physical geometry represented by the coordinate system. In fact, when you have an angular variable, often it makes sense to think of it as a rectangle in that angular variable. Just trust the numbers. And the interval in r goes from 0 to cos theta. So at every theta, we go from r equals 0 all the way up to r equals cos theta. And, because it's always good just to be aware of this, positive signed direction. So our integral is sweeping out this region by moving across here, and at every point integrating from 0 to here. So it's going to keep shrinking. Not a circle if we make theta one of our coordinates. Okay, so I want to draw the exact same picture, but all I'm going to do is use the inverse function. So my interval in r is going to be 0 to 1, because this is the region I'm going to sweep along, is up here. And that at every point, I'm going to integrate horizontally. Positive sign direction, and as I insinuated before, theta is equal to the primary branch of arc cos of r. And you can see this is just the inverse function of this. If you're a dab hand with inverse functions, you can often construct these without a picture, but you often want to draw the picture anyway just to check that your directions are right and that you don't have some kind of weird not one-to-one kind of function. So this goes from 0 to arc cos of r. And that will work. We can do this integral, and it will all be fine. I've prepared this picture, and I've set up the integral we're about to do. And the rest is just integration. I am about to integrate arc cos. If you have forgotten how to do that, here is a little primer. I never remember this, and I had to look this up, so I wouldn't ask you to remember this either. Integral from 0 to 1 of cos I would expect you to be able to do. Sine of theta, 0 to arc cos of r, dr. And this is showing you what sine of arc cos is. So sine of arc cos, it turns out, is the square root of 1 minus r squared dr. And this is just single variable calculus. In case you've forgotten, and it's almost like I'm doing this because I'm going to come back to this idea later, you can do a change of variables to do this. And what is integration by substitution other than just the inverse operation of the chain rule? So you invert the chain rule, and what you get in our new coordinate system is pi on 2 cos squared theta cos squared phi d phi, which is pi on 4. Isn't it nice that the chain rule is so very easy to invert in one dimension? We'll come back to that idea. It's not a coincidence that I picked a very obvious polar notation for this integral, but there is nothing in these 2 pages that suggests that polar coordinates are special. It's just an integral. You just sketched it out. It didn't even look like a circle. It's just a function. This is not a circle, but being able to work in these coordinates is quite helpful. We will come back to polar coordinates later and many other coordinate changes once we understand how to do this in a more complicated setting. But for now, we're going to say that's all cool in R2. Triple integrals. I mean, same thing. Like, absolutely the same thing, but you have to start getting a bit careful. So now, I want to integrate over a rectangular prism. Basically, everything I've taught you is the same. You just have an extra layer of iteration in the proof, and also it's a little bit harder to imagine what it means when you do things like compute what the Riemann sum is. So just take all the proofs we did, increase their dimension by 1, and then draw a box, and you're in pretty good shape. Okay, so what does this integral mean? Well, we start by integrating x from p to q. So x, why did I do x from p to q? We're going to do x from a to b. X goes from a to b. And then we do y goes from c to d. And then we have our new friend z that goes from p to q. Integration bounds on a prism can be freely exchanged, just like integration bounds on a rectangle. However, now that we have 3 of these, we had 2 different possible orders of integration here. How many different possible orders of integration do we have here? Thank you. I wanted you to say 3. No, 6. There are 6 different ways we can do this. So, of course, things are getting a lot more flexible. We have a lot more choices. So, this is all fine. You play around with the numbers. You interchange freely on a prism. As we know, not every shape is a prism, just like every shape was a rectangle. But as we also know, every shape can be a prism, just like every shape can be a rectangle. So the theory holds, and we can have bounds. So if I want to integrate some weird shape, I'm going to say I could integrate from x equals some function, which I'm going to call phi1 of y and z, to phi2 of y and z. So my innermost integral is free to depend on both of the variables outside it. My next one might be y equals psi1, but it can only depend on z. It can only depend on the leftover variable, to psi2 of z. So this goes outside. And finally, z has to go from some constant to some other constant. So it's important that you get these orders right. So this can depend on y and z, the 2 integrals left to do. This can depend on z, but not y, but not x, and these have to be constant. And of course, all the usual properties we've come to know and love still apply. You still have linearity, you can still add regions. If you just take the integral over some volume W, then the integral is the volume of the region. Nice and easy. We'll do one last example and then we'll call it halfway. We're going to calculate the volume of a sphere. You've probably done this before in your life, but not this way. So I have my sphere, and I want to calculate the integral over this region, and my integrand is 1. dz dy dx. From symmetry, it's completely immaterial what order we do, so I shook them around and decided to do z first. So, my z interval is going to be integrating up this way from -1 to 1. And at each of these heights, I'm going to do a two-dimensional integral. So at each of these, I'm going to integrate some area like so. And you can see that this area changes size as I move up and down the sphere. So at the start, it's quite small. At the start, I integrate this tiny thing, then it comes out and becomes a much larger integral, and then it comes back to 1. So I've got my x interval, it's between -1 and 1. That's nice and easy. We'll do my y interval now. So I'm going to say, well, where is y? Y is this bit. And remember, these bounds are allowed to be z-dependent. So y is going to go from here up to here, which is to say, y is allowed to go from minus the square root of 1 minus z squared to plus the square root of 1 minus z squared. And this kind of comes back to the question you asked about the plus and minus. These are both inversions of the same thing, except we just choose a plus for one and a minus for the other based on our geometric understanding of the region we are interested in. So we have our y interval, and hopefully, and I'm leaving this to you, you can go and figure out that your x interval has to be this. How did I get this? Well, I remembered that x squared plus y squared plus z squared has to equal 1, and both z and y are free, so I just have to express x in terms of z and y. And what that gives me is my final volume integral. X equals the square root of 1 minus y squared minus z squared to plus 1 minus y squared minus z squared. Y goes from minus square root of 1 minus z squared to plus the square root of 1 minus z squared. And z is fixed from -1 to 1. So x is allowed to depend on the other two in just the way that the function tells us it should if we're on the boundary. Y is restricted to this horizontal line, and it can go from -1, that thing, to that thing. And z can go from -1 to 1. And you can see at each level of the integration, I'm going to lose my dummy variable. Here I'm going to integrate away x, then I'm going to integrate away y, and then I'm going to integrate away z, and I don't undo that by having the wrong variables in my integration bounds. Yeah, this is the way you should always do y and z. Oh no, I kept them. No. The next one is just you drew a line. Oh yes, I most assuredly did. No, it doesn't matter. It doesn't matter. Well, no, the picture should be right. I'll fix that up during the break. All right. So we do the calculation because math is lovely, but if you don't get a number at the end, you've kind of wasted a lot of your time. Spot the applied mathematician. 1 minus y squared minus z squared dx dy is equal to the integral from -1 to 1 of 1 minus z squared over 2 times pi dz, which is equal to 4 pi on 3. You do the integrals yourself. I did it, so you can do it too. If you have printed out the notes, you will have noticed that there is another example next. I have "if we have time" written in giant letters, and I think you all actually need a break because this has been a bit of a heavy one. So I will actually put up the work solutions for the next example, but probably I won't do it in class. All right. Take 5 and be back. We'll start on the hour-ish. 1 second. Yes.
You know, for the
dy dz, thank you.
that's like
Say again? It's very loud.
that, like how come that's
Sorry?
like here it's all one.
Yes, but you don't have to put in a 1. It's understood that if you don't have a thing in there, it's just a 1. Because that's the natural operation. I mean, you can write a 1 in here if you want, but if you ever have an integral and it doesn't have anything inside, it is 1. Because when you integrate 1, you get the volume. By definition. Just like when you integrate 1 on a rectangle, you get its area. I don't know what to tell you. The point of an integral is to calculate volume and area. Yep. Next question. Yeah, so we're cutting it for z, and then we integrate on the vertical line. Yeah. Yeah, in a sense, we are. The y is restricting us to You can plot xy equals something, but xy is an equation. There's no z notation. It's not like z equals xy. I mean, you could put an x function, but it would have nothing to do with it.
Oh, so you know when you're calculating
Yes, yeah, I mean, that is true. Yeah.
well, I'm just thinking if we're calculating
We can be thinking of calculating the volume, but we're really evaluating the integral of the function. It is what the volume under xy would be on that thing. But as you get to higher dimensions, that becomes a harder perspective to hold. Yeah.
I don't understand how we're calculating the volume.
I mean, we're calculating volume because we're integrating one. You integrate 1 over a rectangle into the area. I'm going to go back to something we talked about yesterday for one variable calculus. If I integrate over a rectangle, if I integrate over I get a constant.
We just want to point something out.
Probably is, yeah.
Yeah, probably.
Yeah, otherwise it's like 1 over root 2, so kind of confusing.
Okay, let's bring it there. Let's bring it in. I love that you guys are enthusiastic and asking lots of questions, but I also need like a minute in that gap for myself too. So if I tell you that it's no more question time, understand that you get a break, I also need a break. A couple of important points that were raised though. The first is, wait, how are we calculating the volume or the area? So remember, with multiple integrals, we established a property, which is that if you integrate a constant, then the integral is the constant times by the area of the rectangle. Okay, that all made sense. The same is true of our prisms. In this case, in our triple integral, this is pi on 2, by the way, which was also pointed out to me. Happily, I got that right in the integral below, so that's good. Same here. If f is a constant, then what you get is that constant times the volume of W. So to get the volume of our sphere integrated, 1 being the constant. When you have an integral that doesn't have a written integrand, it is integrating 1. So that is just notation. You will see that again in your life many, many times over. So it is totally okay just to write this to mean the integral of 1. However, since you might not have seen that before, I will write that explicitly here. So, to calculate the volume of the ball, we integrated 1, because even though what we said was true for a prism, it is actually true for any shape you integrate. Integrating 1 over a volume gives you that volume because you are adding up all the little cubes. Okay, good. Seems like the hard part is probably out of the way. The next example that I didn't do is find the volume of 2 intersecting cylinders. I can't think of any reason why you would ever want to calculate this, but have a go. It's quite neat. Your intervals are this. You'll notice both your y interval and z interval depend only on x. That means that they can be swapped freely. It also means that the cross-section in x is a rectangle, which is quite neat. Actually, in this one, it's a square because they're the same. So if you took a cross-section here, what this result would actually show you is that that cross-sectional shape is a square, which I would never have been able to guess. So that's nice. Tackle this one yourself. It is a nice little test of your geometric understanding of the shapes. However, I want us to get out of here on time. We're going to move on to what is probably the last big idea in multiple integration, which is changing variables. Okay, so I have this integral here. You can set this up with everything you know how to do. It's a bit annoying, but you could do it, because you could say, all right, as long as I'm going to sweep vertically from 0 to 3, and then, depending on how high I am, if I'm less than 1, I will integrate from x equals minus y across to x equals y on 2. And if I'm between 1 and 2, I'm going to integrate from whatever that point is to that point. And if I'm above that, I'm going to integrate from that to that. So you can see there are 3 different regions I have to integrate over. It's a bit annoying to do. If you're watching at home and not in my classroom, then the penalty is you now have to pause the video and do it. And now that you've done that, let's keep going. This is a bit annoying, and it seems like this might be a bit easier if we change up the coordinates. What if I instead say, well, I can see that on this particular line, y minus 2x is constant, it's equal to 0. And on this particular line, y minus 2x is constant, it's equal to 3. So what if I make one of my variables y minus 2x? Or if you like, oh no, we'll get that in a moment, in which case it looks like instead of integrating from who knows what to who knows what, I'm going to be integrating from 3 down to 0. Okay, that might have improved things. And actually the sweep doesn't look too bad either. Because here I have y plus x is equal to 0. And here I have y plus x is equal to 3. So I can just sweep up this direction. And it looks like it should work. So if I let u equal y plus x, then I'm going to need to be able to write x and y in terms of this. I'm going to close that because that is going to annoy the heck out of me. Nope, takes more than 2 seconds to work out, so I'm not going to do that. Okay, so in that case, x is equal to 1/3 v minus u, and y is equal to 1/3 u plus 2v, which means, okay, I'm just going to naively do my integral this way. Okay, so I want to go from u equals, and you can see I'm going from 3 to 0, so I've been nice and careful about this. And I'm integrating from v equals 0 to 3, and I get 1/9 v minus u plus 2v, I'm going to say du dv, and what I'm going to get is 3 over 4. Something isn't quite right here. This was 1/4. This is 3/4. I've lost a factor of 1/3. And that's because what I have done is an attempt at this. But I didn't do all of it, right? Because I have to change my differentials as well. I can't just change my dx and dy into a du and dv. I have to scale them. And that scaling is nice and easy. Let's recall first year and remember how we did it then. So in first year, we remember that when we do something like this, what we're actually doing is the chain rule in reverse, which means it's very easy to figure it out. So I get this integral. I say let u equal x squared plus 1. And because of the domain, I'm going to say x equals the square root of u minus 1. All right, so that's nice and easy. This goes from being x equals 1 to u equals 1 squared plus 1, which is 2, to u equals 2 squared plus 1, which is 5. And then I get x, and I make my substitution. This square root of x squared plus 1 is square root of u dx. Okay, fine. So I've dealt with the bounds, and I've dealt with the square root, but I have not dealt with this x or this dx. Keeping them both was a smart decision, it will transpire. So we need to deal with the dx, and we go back and we go, all right, well, we know that du dx is equal to 2x. So if you like, du is equal to 2x dx. And this is what we did not do. We didn't do this. Chris, that's pretty easy. You've just got to remember how to do that. So we evaluate the integral, u equals 2 to 5 of a half root u, 2x dx equals the integral from 2 to 5 of a half u du, which you can calculate as 21 over 4. And possibly, if I'm lucky, I can calculate it that way too. So we want to change variables in a double integral. We don't want to just change u or v, we want to change both. Now, we had no problems with this before, but that was because we reduced it to a single variable and then changed the order, and then changed the differentials. However, if we want to map our region R2 to some other region in R2, then our map is two-dimensional, and we can't rely on the single variable chain rule. Integration by substitution is the chain rule in reverse, and the chain rule is much more complicated when you have multiple variables. That is good. If this was easy, then there would be nothing to do for the next hour. So, in 1D, you let x be some function g of u. If you weren't aware that this is the chain rule, hopefully this convinces you. The integral from a to b of f of x dx. Get the pullback of your integral bounds, f of gu, g dash u, du. And that is the chain rule. Well, there is a chain rule that looks very simple in 2 dimensions. It just uses something very important. Remember, right back in week 2, distant days, we actually wrote the chain rule in terms of matrix operations. And we started talking about the Jacobian of a transformation. Well, we're transforming from a 2-variable region to a 2-variable region, so it should not surprise us that the Jacobian is about to reappear. So if we define a 1-to-1 mapping, which avoids any issues regarding sign and the like, of region R in the UV plane to some new region R in the XY plane, so that we have a Jacobian UV, which is equal to, as you can recall, the determinant of xu, xv, yu, yv. And that determinant is not 0, so our transformation is nice and always 1-to-1 and well constructed. Then the integral transform is the integral from my old region R to my new region R tilde of f of x of uv, y of uv. So this is going to be a function of u and v, because it's f of x and y, but x and y are functions of u and v, times by the absolute value of the Jacobian, du, dv. So this is the absolute value of the determinant. That thing is always positive. It's just a scale factor. We aren't going to prove this, but we will explain why it works in a way that could be turned into a rigorous proof with a few extra careful bounds, but we don't want to lose all day. So we're going to explain why this works after we've seen it work on our example. Okay. So we're going to do what we did before, but we're going to be a little bit more thoughtful around it. And we're going to say, all right, we got our transform here, right? This was 1/9 v minus u plus 2v. But now we're going to put in the Jacobian of uv, du dv. And this will get us out of our little bind. So we calculate the Jacobian. It is the determinant of xu, xv. Hopefully you are sick of this after this week's tutorial. Determinant of xu, yv, yu, xv, which is equal to, I'm just going to do horizontal bars for the determinant. I think I've made my point. minus 1/3, 1/3, 1/3, 2/3, which is equal to minus 2 over 9, minus 1 over 9, which is equal to minus 1/3, which is good because this is 1/9, v minus u plus 2v, and now we get the absolute value of minus 1/3, du dv, which is, of course, just 1/3, which gives us 1 over 4 as expected. It shouldn't shock us that inverting the chain rule requires the appearance of the Jacobian. The chain rule was the reason we introduced the Jacobian in the first place. And it is the scaling of the differentials. And that's quite nice. That actually gives us a hint as to why this works. But let's quickly generalize this and not just do 2 and then at the end wave at the higher dimensions. In 3D, exactly what you would think, except we now have the 3D Jacobian. I'm sure you can imagine what the condition is in higher dimensions. xu, xv, xw, yu, yv, yw, zu, zv, zw, and we need that to be 0 in our new region R. But Chris, what if I can come up with a clever change of variables that reduces it to something that only has 2 variables of dependence? What if I can map x, y, z to u and v? Well, then you need a w in there. This has got to be square. You need a determinant. W won't do much, but you've got to keep the number of variables constant for everything to work out okay. It essentially just technical. If that's a strange thing, don't worry about it. But if that was a burning question in the back of your mind, then that's the answer. Yep. Yes, we are absolutely going to do that.
Do you have a problem with it with the direction of the group?
No.
Direction of the integral changing around itself, like on a road.
So this is a question about the direction of integration. Look, you've got to be careful to make sure your signed volumes are the same in the setup. That's nothing to do with the math and everything to do with the setup of your integration. So don't lose sleep over that. I also wouldn't try and trick you on that, and in fact wrote one particular question extremely carefully to avoid that very specific issue. So you do enough of those and eventually you're like, oh, I've lost a sign somewhere, probably something has flipped, whatever. But like, if you're very, very careful with your absolute values, then that shouldn't happen. Okay, so in that case, our new integral becomes the integral over our mapped region, over our unmapped region, of f of x of uvw, y of uvw, z of uvw, absolute value of the Jacobian, now in 3 variables, du, dv, dw. Let's move this over so it looks like I planned this out quite carefully. Let's move this down so it looks like I can write in a straight line. It does not, I have not managed that deception well. Okay, so this shouldn't come as a huge surprise. This is, of course, the 3D analog of dx mapping to g dashed of u du. And this should come as even less of a surprise when you remember that we flagged that this might happen when we wrote the Jacobian as partial x, partial y, partial z, partial u, partial v, partial w. So in some sense, if you write that as, you know, d of u and v and w, well, this is the natural thing that seems like it should go in front of it. And it is, because it's just a measure of how much your transform stretches and squeezes space. That's what the Jacobian is doing here. And in fact, that's why our little demo, our quote-unquote proof-ish thing, is going to explain why this happens. We aren't going to prove this. You could. This is something in your power. But we will explain why. We'll give you the moral of the proof. And the key idea is that the Jacobian is a measure of how much space scales under your change of variables. Which makes sense because the determinant was nothing but the the scaling of space under a transformation. And in fact, I would wish that I had written the word determinant there. The determinant measures how much space scales under a linear transformation. So if I have some parallelogram, bit of linear algebra, and I apply some linear transform t, then it might map my vector A to, say, here. So this is TA. And it might map my vector B to, say, here. This is TB. Well, my new parallelogram, copy, paste, is this. And my new parallelogram region is this. Hopefully by now you know that when they told you, ooh, the cross product is the volume of the parallel pipette, what they really mean is it's how much volume scales. So this area is equal to the absolute value of the determinant of t times by the original area. It's the scale factor of area. And now we see why we don't care about sign, because remember, if you've forgotten, the point of the sign of the determinant tells you about the parity of whether your 4 points have rotated. So if you number these 1, 2, 3, 4, and 1, 2, 3, 4 remain clockwise, then the determinant will be positive. But if 1, 2, 3, 4 turn into being anti-clockwise, then the determinant is negative. So hopefully you remember that from linear algebra. The magnitude of the determinant is how much space stretches or squeezes under a transformation, and the sign is the parity of the transformation. We don't care about parity. We're taking care of that when we pick our bounds. So all we care about is the area. But of course, we built our regions out of small rectangles, so we're in pretty good shape. But our problem is that our transform is not necessarily linear. So why does this still apply? Well, it applies because our rectangles are very small. We're going to say that is uv, and we're going to put this corner at u plus delta u, v plus delta v. And we're going to apply some t, which is perhaps not linear. Question mark. And we want to know, well, what is the area? Question mark. But of course, our rectangle is going to be small, which means this delta v and this delta u will be small. And that means that we can start to do things with approximations. Okay, so we built our region. It looked like this. Here's the exact picture we had before, except I'm going to say, all right, area of this rectangle is delta u, delta v. And if delta u and delta v are small, what I contend and what we're going to show is this is approximately a parallelogram in some mathematically well-defined way. So this didn't look like a parallelogram, but let's keep things pretty small. Okay, so for sufficiently small delta u and delta v, and all of these sufficiently's and approximately equals to's are the things that you would tighten to make this rigorous. This is approximately equal to x of uv, y of uv, plus the first term in the Taylor approximation, which remember is h times the gradient, dotted the gradient. So we have grad x, grad y, delta u, delta v. Okay, but remember, these are vectors themselves. So what I'm really saying here is this is grad x dotted with delta u, delta v, and this is grad y dotted with delta u, delta v. Okay, so this is an approximate. There's a plus dot dot dot. Making this rigorous means pulling in Taylor's theorem and bounding the error, and that's the bit that we're not going to do here, but it's a good exercise if you ever wanted to. Okay, so this is going to become x of uv, y of uv, and this becomes the Jacobian. Remember, grad of x times delta u, grad of x times delta v. Well, grad of x is nothing more than xu xv delta u, and this is yu yv delta v plus dot dot dot. Let's move this over slightly. Put it in a box even. Okay. And now what I'm going to do is I'm going to jump this over to this side and say, okay, well, what is the difference between the x in my top corner and the x in my bottom corner? So what are my opposite edges of my opposite points of my parallelogram mapped to? Well, that is simply going to be ux, uy via good, that's a mistake in my notes. xu, xv, yu, yv, delta u, delta v. The difference between those things, if I expand these out as a two-dimensional Taylor polynomial, is simply delta x, delta y. Hey, I'm talking over people a little bit. xu, xv, yu, yv, delta u, delta v. And you can see that as long as delta x and delta y are small, my transformation is approximately linear. This is my t. Approximately. So from linear algebra, we know the area of the mapped rectangle. It is nothing more than the determinant of the Jacobian, absolute value, delta u, delta v. This is the moral of the rigorous proof. Making it rigorous just means bounding all your errors carefully, but the guts of it and the reason why it works is because the first term in the expansion, the Jacobian, is the first linear approximation of the transformation. So this is the linear approximation of t, which, considering we are only caring about a teeny tiny little rectangle, is an appropriate approximation to make. The error is going to be smaller than delta u squared or delta v squared, and since they are very small, we can ignore them. Since the map is nonlinear, the absolute value of the determinant of j depends on u and v. So the transformation of this rectangle is not necessarily the same as the transformation of this rectangle. So if I transform them via my gross nonlinear transformation, t, I might get that my green rectangle changes its angle a little bit, but maybe it doesn't change its volume, and here I get that the determinant of j is equal to 1. But maybe this blue one stretches out a bit more, and I get the determinant of j is equal to maybe 4. Now remember, these areas are still small because the area is this times by delta u times by delta v. And this area is 4 times by delta u and delta v. So as long as delta u and delta v are small, these are still appropriate appropriate parallelograms. Which means that the area of my entire region, the integral of my entire region, is the sum over all of the tiny little parallelograms, each of which has an absolute value of a determinant j of uv du dv, because this is nothing more than the sum over tiny rectangles. We'll just say tiny rectangles. We won't get in the weeds here. A careful proof can be built on this idea. There's nothing that the proof has that I didn't show you other than a bunch of bounding things. QED-ish. That is a very generous use of the box. Okay, we'll do an example because That's kind of the theory. Everything else is now using it sensibly. And it's quite a famous example. Has anyone seen this derivation before? Hands up. A few of you. This is really neat. It's perhaps not as instructive as some other examples I could have written down, but it's nice and introduces a coordinate system that we might find to be quite useful. So I want to evaluate the integral from minus infinity to infinity of e to the minus x squared. I can't do that single integral. So what I'm going to do instead is do a useful double integral that will tell me the answer to this single integral. Because remember, in single integrals, I don't have a lot of freedom to pick things. But in double integrals, I can start changing my coordinate system, flipping my integration, and essentially kicking this integral until it gives me what I want it to know. So what I'm going to write is I'm going to let I be this integral squared. Okay, slight thing we need to address. We are going to do an improper integral. As you know, there's a little bit of theoretical overhead to derive improper integrals, but then they work and you never think about that overhead again. We're going to skip that overhead and say it's all the same as in one dimension, except you iterate it a few times. So, improper integrals, minus infinity to infinity, absolutely fine. You can remember it's a limit if it bothers you. Okay. So expanding that out, I'm going to write that as the integral from minus infinity to infinity of e to the minus x squared dx times by the integral from minus infinity to infinity of e to the minus y squared dy. And then I'm going to do what I can do with multiple integrals. And remember that this is a constant with respect to x, and this is a constant with respect to y. So I can actually lump those things in together. I can move one integral inside the other, and I can get this to be integral from minus infinity to infinity of e to the minus x squared plus y squared dx dy. So what have I done here? I've said this whole thing with respect to y is a constant, and therefore we can move that whole thing inside the other integral. Constant with respect to y. Move inside the second integral. So, I mean, it doesn't look like I've made things better. I've gone from one integral I can't do to a different integral I can't do. But now I have a few more tools at my disposal. And now you think back to 1962 when I think it was Milena taught you about polar coordinates. And you're like, polar coordinates probably want an x squared plus a y squared. Yeah, that is a very smart change of coordinates. And it's going to be doubly smart for a reason I'll tell you in a moment. So for those who may have forgotten their polar coordinates because it was in the distant past of 2025, x is equal to r cos theta. Y is equal to r sine theta. So this point here, which was at xy, is now at r theta, which geometrically, this angle is theta, and this length is r. So, we now want to know what our region maps to. Whoa, okay. Well, I want to get the whole region, and there was a critical little detail in these theorems. I needed my mapping to be 1-to-1. So I can't just say theta goes from minus infinity to infinity, r goes from minus infinity to infinity. That will absolutely cover all of x and y, but I'll do it again and again and again and again and again, and it certainly won't be a 1-to-1 map. So I just got to be a bit smart, and I'm going to say, well, I'm going to let r go from 0 to infinity, and I'm going to let theta go from 0 to 2 pi. Because remember, my map has to be 1-to-1. On my domain. So we can't go past 2 pi, or else our map will no longer be 1-to-1. The calculus of multi-valued functions is very interesting and well beyond anything we will do in this course. Yes, so our maps have to be 1-to-1 for everything to work. And now it's just a matter of the churn. The hard part is the setup. whenever we do a change of variables, first thing we do, you don't even think about anything else until you've done this. You come up with a change of variables, you calculate its determinant, Jacobian. So xr, x theta, yr, y theta, which is equal to cos theta minus r sine theta, r cos theta. I evaluate that determinant and I get r cos squared theta plus r sine squared theta, which is equal to r. So now I've got my determinant. It is r. I want the absolute value of my determinant, but r is always positive, non-negative. So, as will be the case in my integral. This is going to go from the integral, I will do r first. So theta on the outside. Theta goes from 0 to 2 pi, and r goes from 0 to infinity, of e to the minus r squared, absolute value of j, which is nothing more than r, dr d theta. R dr d theta is going to be a transform you sear in your mind. You will do it forever. You will never forget it. It'll be the one thing you remember in like 20 years. It'll be like the mitochondria being the powerhouse of the cell. 2 pi. But now we have an r here, and this is actually an integral we can do. So we have an r here, and now we can do a variable transformation, because I can let s be r squared, and I can do a single variable transformation. I'll let you integrate that yourself, but you get minus e to the minus r squared over 2 from 0 to infinity d theta, which is, you can hopefully see, a half, 0 to 2 pi of a half d theta, which is equal to pi. We could not have done that in this coordinate system. It's not that there's a way to do it here, but it's hard. It's that you can't do it algebraically. The algebraic way to do this is to move it into polar coordinates. And of course, since I squared equals pi, we have I equals the square root of pi, which tells us a fact you've probably met before. E to the minus r squared dr, x squared dx, is equal to the square root of pi. To solve this, you needed to kick it into a two-dimensional integral. It bugged me for a really long time that there is no single variable way to do it. There is no single variable way to do it. You cannot get this answer in one variable. Annoyed me as a mathematician, but what are you going to do? Okay, let's see a useful property which will be helpful. Sometimes calculating Jacobian sucks. And then what we'll do is we'll talk a little bit about 3D, and I'll get you out of here on time. Here it was pretty easy to see the map based on stuff that you know. As soon as you see x squared plus y squared hanging out together, you probably have a gut feeling that you're looking at an r squared. Maybe polar coordinates are helpful. Sometimes this is not so nice. So sometimes it's easy to pick the map, but calculating the inverse, and therefore the Jacobian and all of these things, is quite hard. However, there is one result about Jacobians that we can use, and this comes from linear algebra, which is, if I map this way, the area is going to, the map is going to be 1 over the area, right? So the determinant of the inverse, the determinant of T inverse, must have absolute value 1 over the scaling factor. Taking this to its logical conclusion, we get the very useful rule, partial u v partial xy times by partial xy partial uv is equal to 1. I got asked a very good question the other day, which is, can we assume partial y partial x times by partial x partial y is equal to 1? And the answer is no, because it's not a complete picture. But as long as u and v and x and y are your full set of variables, then you can make this assumption. So you just need to make sure you have all the variables and then this does behave in the usual total derivative way. So which is to say, if we can get the Jacobian one way, we can get the Jacobian the other way. All right, let's look at this much more horrible thing. I've got the integral over a region R of y over x gross. R is bounded by x squared minus y squared equals 1 and x squared minus y squared equals 4. Gross. Sometimes you've got to look at what do I want to make easier. And the things I would like to make easier if I had a wish list is this bound. Seems unpleasant. And this seems fine. This integrand. I've got two variables to play with. So I'm going to say try out u equals x squared minus y squared, which gives me easy bounds. Because instead of integrating from this curve to this curve, so from here to here, I'm just going to integrate from u equals 1 to u equals 4. So my u bounds are going to become vertical. So that's nice. This sucks. Let's make that better. Let's try v equals x over y, which gives me an easy integrand. You have so much freedom when you have two variables that you can often just transform out everything that's difficult. Nothing is free, there's a price to pay, but our new bounds become u lives in 1 to 4, because we have this thing being u equals 1 and this thing being u equals 4. And v lives in, okay, this is not so nice. Kind of is, because of course we can take the x over to the other side and get y over x is equal to a half. And this is obviously y over x is equal to 0. We don't have to worry too much about x equals 0 because we never get to it. So our v range is from 0 to a half. So this is v is equal to a half, and this is v is equal to 0. So I've mapped this unpleasant region to a rectangle. And rectangles are nice for any number of reasons. We can switch the order of integration freely. Also, they tend to be easy to calculate. So we're doing this integral. First thing we do before we do anything else is we get the Jacobian. Like, don't do anything until you have it. So our Jacobian, partial xy, partial uv is equal to xu, xv, yu, yv. The problem is I have u in terms of x and y and v in terms of x and y. What I don't have is x in terms of u and v and y in terms of u and v, and that is a little bit more of a pain to get. If you want to convince yourself that if you choose all your signs correctly and such, you get this. But this is not true everywhere. It is true in our region, but the sign choice manifests elsewhere. Maybe the mapping is not one-to-one in other parts of the domain. You've got to be a bit careful. I don't like being careful. I like it when things just work. So what I'm going to do instead is use that little trick to find the Jacobian. I'm going to say it's pretty easy, however, to find partial uv, partial xy, which is equal to ux, uy, vx, vy, which is 2x minus 2y minus y over x squared and 1 over x. You can all calculate that, which gives me 2 minus 2y squared over x squared, which is 1 minus v squared. This is actually a place a lot of people go wrong when they write up solutions, is they forget to write their answer in terms of v. Don't forget this. It's an easy mistake to make, and you're currently going, I'll never forget that, and in the exam you will forget that. Don't forget to turn everything into the variables you want to work with. Okay, so our integral wants us to get the Jacobian xy uv, but that's easy. That is just 1 over 2, 1 minus v squared. And in our entire domain, that thing is always positive. You can check this for yourself if you want. So our integral becomes the integral from v equals 0 to a half, the integral from u equals 1 to 4 of v, which was our integrand, y over x, and then absolute value of our Jacobian, 1 over 2, 1 minus v squared. So this is the absolute value of j, du dv. And this is particularly nice because u vanishes entirely. So you can just multiply this thing by 3 to deal with the u integral, and you've got an easy single variable integral that you can do with partial fractions or type into Mathematica. Type into Mathematica. Good. This is a one-to-one map within our domain. However, we chose our domain carefully to ensure that would happen. This is not a one-to-one map everywhere in the R2. So just be a bit careful, make sure your map is one-to-one. All right. Common useful coordinate systems. Hey, physicists, pay attention. Everyone else should too, but especially physicists. Polar, we just met it. Polar looks like this. And of course, as you learned, the Jacobian is R. Good. Like, memorize that forever. However, the important ones are in 3D. So cylindrical coordinates are polar in x and y, but z is allowed to freely vary. We actually saw in last week's seminar that we saw the helix. That is actually a really nice example of something that's very easy to represent in cylindrical coordinates, because you just have r being constant, theta changing linearly, and z changing linearly. So, the derivatives calculate the Jacobian out. Just x is r cos theta, y is r sine theta, and z is how high you are. Okay, good. So, calculate out the determinant. Cos theta minus r sine theta, r cos theta, which is exactly what we had before, except we have a whole other row and column, except it's very, very easy, 0, 0, 0, 1. So if we take our determinant and index it off this point rather than the usual top corner, it is trivial to see that that is r. Or you can calculate it out. Question? No, because you're in 3D. You can't ignore the z, but it doesn't do much. However, we're about to move when it does. But I want to be very careful about answering this. You really want to have that third variable. Even though it doesn't appear in the algebra, like remember, determinants need to be a square matrix. So you want to have that there. Question? So you restrict it quite carefully. What it really means is you don't want your thing to be blowing up at 0, otherwise you have problems. We are going to gloss over that a little bit. You don't want it. Improper integrals with 0 you have to be a bit careful about. So we will see examples in vector fields of things like 1 over r, and you just want to be a little bit careful with polar coordinates, but mostly 99.99% it's fine. If there is, it's something I haven't thought about in a very long time. It tends to be something which, again, it's not going to be multi-valued unless there is a discontinuity at 0, at which point you have problems. So if you have a continuous function at 0, and remember, we're assuming plenty of continuity on everything, then it will be fine, because whichever direction you approach it from, it will behave the same way. Where you're going to run into real problems, and it won't be a problem because your issue is only on a set of measures 0, is if you have a jump discontinuity at 0. We're not going to do that, but you will meet functions like that in your life. If you have a problem in an integral on a single point, it tends not to be a problem, but you need measure theory to prove that. So the answer is measure theory. Okay. So, final coordinate system, and the one that you're all going to hate. Let's quickly finish this up. I'm going to power through to the end, so because I want to get you out on time. So if you have questions, perhaps bite your tongue. Just until we get to the end, and then I will allow the leftover time for questions. This is always positive. Spherical coordinates, everyone's favorite, 2 different angular directions. The first direction, and here is the place this is the only time in your life that I will let you orient your coordinates this way. Otherwise, do it right. X to the right, Y to the top. But it is easier to see what's going on in spherical coordinates if I swing X out of the screen. So it's not nice, but it gets the job done. We have 2 angles now. So you've got a coordinate rho, which is your radius. So let's say I'm looking at this point here. Well, it has a radius, which is rho. And it has an azimuthal angle, which is the angle away from the xy plane. So here is my azimuthal angle, phi. So it is how much up or down I've gone. And that azimuthal angle is between 0 and pi. Right? Because if I swing, as we'll see in a moment, if I swing over, then, minus pi to pi. Minus pi to pi. And again, we don't really care about sets of measure 0, but just because of what I said before, let's make that minus pi to pi. So azimuthal angle can go from below to above, but it can't swing all the way around. And the reason it can't swing all the way around is because we have our third coordinate, which is theta, which is the angle away from the x value, which goes in our usual two-dimensional, our usual polar angle. So theta is your polar angle, but your azimuthal angle is a bit different, and rho is your usual radius. Mostly it is unlikely that you will get thrown a problem where you need to carve out very weird looking shapes. So mostly you integrate over spheres or half spheres or quarter spheres or whatever. Okay, so the Jacobian is this, and you apply a bunch of trig identities, which I will leave as an exercise to the reader, and you get this being minus rho squared sine phi. And this thing is positive, and this thing is positive, and this thing is negative. So our integral is the integral over our mapped region of f in terms of rho theta phi, rho squared sine phi, d rho d theta d phi. Look, when you're actually calculating things, this one tends to get used a lot. If you never plan on calculating things, then you can just kind of forget this. I don't expect you to remember this. I will give you the Jacobians for the standard coordinate systems in the exam because they are standard. If you were sitting at home trying to do it, you could look in a book and you could find them, and you would know to look up spherical coordinates because the thing you're integrating is a sphere. This is not a memory test. This is something I would give you. Okay. Or, I haven't decided yet, or you would write on your one page that you're allowed to take into the exam. We'll talk about the exam later. It's not important now. The end. Next week we will do a little bit more. In particular, we're going to see some places in the world where multiple integrals are useful. And then we're going to move on to line and arc integrals, which is really our pathway into vector calculus proper. Okay, I'll see you in an hour. Before you leave, I just want to say, yes, I've got 30 seconds. For those who didn't catch it yesterday, this is the week where the seminar stops being how to use Mathematica and starts being how does the stuff we learned in class work in Mathematica. So we're actually going to be looking at variants of class questions and seeing how you would use Mathematica to augment what we know. Thank you very much. We did it. We got out on time. You guys are the greatest. I'll see you in an hour.
Whether this
Line up in a line, please. Like go forward. And with questions, and I know.
That's just starting.
That's actually
line. Yes, wait.
Next.
How does the Jacobian matrix give you, allow you to change the variable?
Say what?
How does the Jacobian matrix determine allow you to change the variable?
I think you need to rewatch the last hour. I can't read.
Today's not my day.
Why?
Okay,
First
next
of all, I
question.
spilled water.
If I here be negative pi on 2 child,
Yes.